So now let's start today's lecture. Okay. Let me minimize all the stuff first. Well, okay. So last time we actually stopped right here. Okay, about the egg puzzle problem. Okay. But before we go on with our discussion. Okay. So I actually think about something about. I actually have some thoughts about the our discussion on the depth search with recursion. And I don't know if you ever have this mindset when you learn recursion. Okay. Uh, when you are working with recursion, you essentially is calling the function itself again, right? But behind the hood, what we are trying to do is to try to decompose the problem into a smaller problem. Okay. And in fact, in computer science and data science, we have a technique called divide and conquer. Okay. Essentially, when you're working with recursion, you are actually trying to divide your problem into a smaller problem. Okay. And you keep on dividing your problem into a smaller problem up to the point you can solve it. So this is what recursion, this technique is truly about. Okay. If recursion is really just a function calling itself, then wait, this one, right? No. Then explain to me why I cannot write a function like this. Okay. Technically speaking, this is a recursion. You are calling the function again. You are calling the function itself again. This is a recursion. But why we never write recursion in this manner? And in fact, if you execute this function, the function will give you recursion error. The reason is very simple. Because when you are writing recursion in this manner, you are not really reducing the problem into a smaller problem. You are still having the same problem, and you are asking the computer to keep on calling the function to solve a function without doing any modification to the problem itself. Okay. You want to solve factorial 10, and the way you solve it is I call factorial 10 again. So keep doing this will consume your computer's memory, and that is the reason why this is give you a recursion error at the end. Okay. And when you are working with recursion, it is not just about function calling itself. When you use recursion, the most important aspect of recursion is simple. You try to reduce the problem into a simpler form. Here we are calling recursion, and we are running factor n. But to solve factor n, we decompose factor n into n times factor n minus 1. The factorial n compared with factor n minus 1, factor n minus 1 is a easier problem to solve. We let the computer solve n minus 1 first, and then we take the n minus 1 result times n, then we get the result for factorial n. Okay. So this is the actual principles. This is the actual real principle behind the hood why we want to use recursion in the first place. I don't know if you have learned recursion, the hidden meaning of recursion in this manner. I don't know if you have learned this. Okay. But I believe that it is a good chance for me to introduce properly what recursion behind the hood supposed to be. So I talk about it once again. Okay. Okay. And why I have a discussion like this is because I recall when I was studying for my undergraduate study, I learned the concept of divide and conquer in a algorithm specific course, but not in a programming course. Programming course will just teach you what is recursion, that is function calling itself. But behind the hook, why we do recursion is to do divide and conquer. It is not something that the programming course may touch upon very serious. Okay, it is something that I learned when I was studying for my algorithm course. Okay, but because this course is a programming course, so I think this course is a algorithm course, so I think it is a good chance for us to briefly at least talk about this concept. Okay, okay. So essentially, when you are doing depth first search, you are actually doing the same. You are actually dividing the problem of tree search into a smaller problem. When you are building the search tree, you start off with the initial state, and under initial state, you will have different neighboring states. And what you will do is you will pick one neighboring state, and then you will keep on exploration. And under this neighboring state, when you do exploration, you will also pick one neighboring state of it and do further exploration. For example, the initial state is a rack, and we have Cebu, Sirius, and Timisoara as its neighborhood. And we go to Cebu, and under Cebu, we'll go to Fagras, Otis, and Mitsubishi as the neighboring states. And we'll select the Fagras as the state for further expansion. So under this paradigm, under the depth first search paradigm, we can actually notice something. We can consider this whole process as a red generate a bunch of neighboring states, and we do a depth first search sequentially on each neighboring state. Okay. You can also consider depth first search of a rack as I take the neighboring states of a rack, and then I do a depth first search on each neighboring state sequentially. It is the same, fundamentally speaking. Okay? It is the same, fundamentally speaking. So when we are writing the recursive call of depth first search, we are essentially doing the same. The loop here, highlighted in blue color, is the exact coding segment that is dividing our problem into a chunk of smaller problem. Okay? So essentially, when we are writing depth first search in a recursive manner, we are also trying to do things in a divide and conquer approach. Okay? I hope that this gives you a more understandable overview on the nature of the recursion. Okay, and you can even look at the internet. Okay, if you want, you can find something like this. Okay, you can type down divide and conquer algorithm, and you will find that actually under Wikipedia page, we have one dedicated page talking about the divide and conquer algorithm. So it's not something I randomly give a link to describe it. Okay, it is a category of algorithms that is really being well studied in computer science, okay, or data science, okay. So if you want to have more understanding on algorithm, you can try to use this keyword to do some exploration on your own. Okay. So now we get back to the problem solving. Okay. So in the previous lecture, we actually briefly introduced the missionary and cannibals problem. So in this problem, what we have is having some cannibals and we have some missionaries. The cannibals are actually the tribe that eat human flesh. Okay, the tribe that is the that is people who doesn't have well developed social system. I would say so. I am trying to describe it in very simple, plain English. Okay, tribe is referring to people who have who is undeveloped in social system. Okay, they don't have well established social system, and they are using very primitive technology to live their lives. Okay, in Cantonese we call tribe as 部落. Okay. Okay, so cannibals means 食人族. Okay. Okay, I need to do some Chinese terminology here just to make sure everyone understand. Okay, so cannibals are referring to people who eat human flesh, and the missionaries are of course the mark of a religion who is trying to promote their religion. Okay, but it doesn't matter. It doesn't matter whether whether they are spreading religion or not. This is not our concern. Okay, it is just a character setting in this problem. Okay. So now we have 3 missionaries and 3 cannibals in a riverside, and they need to travel to the other side of the river. And what they have is a boat that only carries 2 people. 2 people. So the issue in this problem is that the cannibals, when they outnumber missionaries in either side of the river, the missionaries will get killed by the cannibals because the cannibal will eat human flesh. Okay. The cannibals will eat people. So if they can overnumber, that if their number is larger than the missionary in either side of the river, they will kill the missionary and they will eat them. Okay? So essentially you need to figure out a sequence of operation that move the missionaries and the cannibals two at a time to the other side of the river. Okay? And you need to make sure that in both sides, if there is missionary, the number of missionaries should not be smaller than the number of cannibals. Okay, so this is what this problem is trying to do. And you may think that how we can solve this problem. And in fact, we can solve this problem by trying to model it as a single state problem. Okay. So here we describe how we do so. For the state, essentially, we need to keep a record on how many missionaries is in the near side of the river and in the far side of the river. So the nature of the problem is that we are trying to transport the missionary from one side of the river to another side of the river. To make our discussion easier to understand, we will say that the original side of the river as near side and the other side of the river as the far side. Okay. Okay. So we need to keep a track. First of all, how many missionaries are there? How many cannibals are there in both sides of the river? Okay. For example, for the far away side, we have 2 missionaries and 2 cannibals right now. And for the near side, we have 1 missionary and 1 cannibal. Okay. So this is the status we need to keep a track on. Okay, but we don't need to specifically differentiate the missionary and the cannibals. Okay, okay, because in our problem setting, each missionary are the same, are substantially the same. Okay, and each cannibal are also substantially the same with each other. Okay. So that is the reason why we don't need to record, we don't need to assign names to each missionary and record which missionary get to the river. We only need to remember how many missionary is at one side of the river, is a near side of the river, and how many missionaries is in the other side of the river. And we do the same for the cannibals as well, and we are able to finish our model. Okay, so here in our problem, differentiating which missionary is not important, so we can ignore it. We can just record how many missionary is in one side of the river and how many missionary is in other side of the river. Okay, and of course we need to know the location of our boat. Okay, so for example, if we already set we already sent the missionary and the carrier boats on a boat to the other side of the river. Then now the boat is in the other side of the river, okay? Meaning that the near side of the river, the missionary and the carrier boats cannot move. Okay, so as you can see here, the missionary and the carrier boats in the near side of the river, they don't have the boat. So the missionary here and the carrier boats here, they cannot move. Okay, they cannot move. You cannot move the missionary and the carrier boats unless the boat is at their side. Okay, so the location of the boat in this question is vital as well. So this is the state that we need to keep a record on. Which side of the boat is, which of the, for the boat, okay? Which side of the river it is located at, okay? And also, for both sides, how many missionary and how many carrier boats are there? And these two factors, these two information are the information we need to keep a record on. Okay? Okay? And then our initial state will be 3 missionary, 3 carrier boats at the near side of the river. And also the boat will also be at the near side of the river. Okay? Oops. And then for the action is rather simple. The action is moving the boat from one side to the other side. For example, if the boat is at the near side, then the action of the boat is go to the other side. If the boat is at the other side, then the action will be go back to the near side. Okay? The action depends on the location of the boat. The missionary and the carrier boat simply cannot move without the boat. Okay? Okay. So any questions? Any questions? Any questions? Any questions? And essentially, our goal is to move all the missionary and carrier boats across the river. Okay? And so the goal is quite clear, okay? We just check whether the other side of the river contains 3 missionary and 3 carrier boats, then we reach our goal. So the goal is rather simple. It is also predefined as well. So when you are plotting the movement, you have several constraints. For example, every people can navigate the boat, okay? The people can, the boats can carry at most 2 people. So you can situation that the boat only contain 1 people, okay? And the missionary can never be outnumbered by the carrier boats at either side of the rivers. So if it is not able to achieve, then both sides of the missionary will get killed, okay? And here is just a showcase on the sequence of actions that allow the carrier boats and the missionary can cross the river. Okay, so can read at home. Okay, I will not go through the steps here. You can just read it at home. Okay, it's not vital for our discussion because our main focus is to create an agent to find this solution. Okay, the solution itself is not that important. Creating an agent that can give me a solution like this is more important. Okay. Then you may ask is how we implement all the things we talk about. Right here. In fact, you can just refer to the PPT here and the source code that I give to you. Okay, but because of the time constraint, I will not go into technical details of my implementation. Okay, because this is not a programming course after all, so I will not spend my time to discuss how I implement this problem into a program that can get executed. But don't worry, if you want to learn how to we actually do the implementation, you can actually refer to the source code that are uploaded to the Moodle, okay? And I also included some comments that will explain the source code right here. And I also included some slides in the PowerPoint to explain my decision in implementing the things that I talk here into actual program. Okay, so the main reason why I released this source code to you is that I want to illustrate one concept. All the things we discussed right here in this course, it is not just thought experiment, okay? Well, after we really define the case, the state, the successor function, the path, course, and the action, we can really implement it as programming language, and you can really execute it. We can really implement it as a program, and your computer is able to solve it. Okay. So one thing, I've already covered this concept already in previous classes, but you will find that one thing in particular is very important. When I am writing the source code for solving this problem, I only write the function that defines the state. I only create a structure to define the states, to record the states. And I also created functions to generate the successor states given a state and given a state, okay? Given a state, I've written a successor function that can generate all the neighboring states and the corresponding action. Okay? And other than that, I did not write any coding to actually compile the sequence of action to get from the initial state to the goal state. Okay, the sequence of action that allow the agent to move from the initial state to the goal state is achieved by the search of the algorithm. If you take a close look on all the coding I write here, the coding here is just to describe the problem. It is not, I have not put any coding within the refer causing problem object that is directly used to compute the sequence of action that allows the agent to move from the initial state to the goal state. No coding is responsible for that. I only write a function to compute any given state, their successor states, and the corresponding actions. That's it. Okay, that's it. That is the coding that I do here. Okay, and I also authority to define the initial state and the goal state and the path course, okay, the step course, okay. But after I define all of them, I don't write anything else. I just take the whole problem and then put it into the problem solver, give it into the agent solver, the uniform call search function that we explained in the past. Okay, and again, if you compare the differences, wait. If you compare the differences between the monitoring problem and the refer causing problem, if you compare the uniform call search algorithm of both sides side by side right here, the right hand side is the refer causing problem, and the left hand side is the monitoring problem. and you will find that the coding between these two source hooks is exactly the same. Okay, is exactly the same. Okay, okay. I only write some customized code for visualization, but the core coding for solving the problem is remaining the same. Okay, so up to now, I want to illustrate one point is that no matter how complicated your problem is, as long as you are able to express your problem as a single state problem, some problem you cannot do so, but for some problem, if you are able to express the problem as a single state problem, and you are able to convert your representation into programming coding, then you can follow my approach and solve the problem. Okay? And the beauty here is that I don't need to design an algorithm from ground up. I don't need to design some algorithm to solve one problem from scratch. Here, I am just merely dividing my problem into a rigid mathematical expression, into a rigid mathematical representation that can be implemented, and that's it. All the coding that I do here is to describe the problem to the computer and let the computer handle the rest. The computer will just try out all the possible combinations and to get to the solution that I want. Okay, but the beauty of this approach is that I am not writing a new algorithm to solve a problem. All I do is describe the problem using programming languages, and the rest is handled by the computer algorithm, the search algorithms. Okay. But of course, okay, nowadays, you may not enjoy this approach because nowadays we have ChatGPT. We can describe the problem to the computer using natural language. Okay, you can just type out your questions in layman English terms, and the ChatGPT or other large language model such as the Google Gemini or the DeepSeek, okay, or the DeepSeek large language models, they can compute the result for you based on your plain English, okay? But in the 1970s or 1980s, okay, able to solve a problem without completely design algorithm from scratch, and you are just describing a problem and let the computer solve it is a brand new concept. Okay, and that's why in the 1970s or 1980s, these are considered as AI. Okay. Okay, but you may ask is Professor, so these things have exist in 1970s and 1980s. So why we still want to learn that? And the reason is because this algorithm is still widely used, but they are used implicitly. You don't even recognize it. Okay, so let me open up this example again. This is my favorite childhood game called the Age of Empires. Okay, and it is substantially similar to some games nowadays. For example, the LL. Okay, when you're playing LL or the Age of Empires, what you would do is you will need to click a character, and then you click in other places, and the soldier or the hero that you selected will move to the places that you specified, right? Right? Thank you. And anyone here who play these kind of games and understand what I'm trying to say? Anyone? Okay. So games like Age of Empires, okay, you will need to control a large army to fight your opponent. So you being the general, you will need to control your troops. To control your troops, what you do is you click a soldier to select a soldier, and then you go to the map and click another position, and then the soldier will automatically figure out the path to go to that location. Okay? Okay. Behind the hood, how computer is able to figure out this path, and the law idea is more simple than you believe to be. Okay, so the idea is simple. The computer have the full map of the game. Okay, so as a result, it knows the obstacles of the game. Of the game map. Okay, so what it will do is it will define some points that doesn't have any obstacles. And then after defining those points in the map, then those points will get connected together as a network. And at the end, you would convert the problem of finding a path for the soldiers to move forward in a game like this into a problem similar to the Romania Turing problem. Okay, in the Romania Turing problem, we have the map of Romania, and essentially we add nodes in the Romanian problem to demonstrate the points, to represent the cities that the agent can go to. Okay, so for those games, how those games AI can compute the path of the soldier, it is done the same way. Essentially, you have the map of the game and you assign points to the areas that doesn't have any obstacle that the agent can move to. And after you specify those points will become a network. And essentially, the formation is the same as the one in the Romania Turing problem. And after we form a map like this, then the remaining problem is to just run a search algorithm, and your soldier will now able to find a route to get to the places that you specify it to go to. Okay? Okay? So you may ask this, Professor, all these problem-solving agents, they are old tech, why we still need to learn them? In fact, they are still widely used, but they are not being promoted as AI anymore. Okay? If we do not have the search algorithm right now, you may not even be able to play your favorite games such as my favorite games such as Age of Empires or games like LL. Okay, those games, why the soldiers know where to go, know how to plot a route to go to the places you specify, is by doing a search algorithm on the game map. Simple as that. Okay. Okay. So these algorithms are not something that is being obsolete again, being forgotten and not used. They are used implicitly in games, in many games. Okay. So any questions? Any questions? And I would say this technique is already well established, that so you would not consider them as state-of-the-art AI, okay? But you can still treat this course as a course to train your ability to understand coding, understand the algorithms, okay? And let's get back to our examples, okay? So here we have the river crossing problem. And we can try to execute it. Now I just run all, and then I select the environment for execution, and then you will see that now it's trying to do its job. And at the end, you will find that it is able to list out the procedures that is involved in solving the Bigelow and Cannibals crossing river problems. Okay, it specifically specify whether the Cannibals is moving from which side to which side of the river. Okay, and is listing out the sequence of actions and the resulting state of the game after the action is performed. Okay. So as you can see here, our agent is able to find a sequence of action that move the missionary and cannibals to the other side of the river. Okay. So any questions? Any questions? And the next question is something that is even more interesting. Okay, for the implementation here, I will skip. But the reason why I put all these slides here is for the students who want to self-learn. Okay, so if you are reading my source, but you don't know what I'm writing, you can refer to the slides here and study it on your own. Okay, but because this is not a programming course, I will skip the implementation details discussion right here. Okay, I will just focus on the algorithm part. Okay. And the next problem we will need to talk about is the X-queen problem. Okay. So in fact, you can even make use of the single state problem to solve some another kind of problem. Okay. In some situations, we want to find a configuration of something, okay, that satisfies some constraint. Okay, we want to find some configuration that satisfies some constraint. Okay. For example, if I am trying to allocate, if I'm trying to allocate the meeting hours with a bunch of students, okay, and the values is having time constraint, okay, then and I also need to take consideration of each student may have different time slots that they are available, okay, so finding out a configuration arrangement that I can meet all the students in the most efficient manner is a problem that is to find a configuration of something that satisfies some constraint. Okay? Okay. And for those kind of problems, we can also use single state problem to solve it. Okay. So let me repeat. In some kinds of problems, what we will want to do is to find a configuration of items that satisfy all the constraints that is given. Okay. For example, I need to have meeting with 5 students. Okay, and these 5 students have their timetable and their available time slot may have conflict. Okay, and I also have my timetable, so I'm not free available all the time. So what we need to do when we are trying to figure out the meeting time for each student, what I need to do is to essentially take all the available time constraint, available time slot of myself and the students, and then try to figure out putting what meeting in what time slot that can maximize efficiency and also not having time collision with the students, within the students. Okay, so for example, if there is time slot, I cannot arrange 2 groups of students to meet me in that time slot. Okay, that is, I cannot have 2 students having the same time slot to meet me. So this is some sort of the time constraint that I need to follow. Okay, and in this kind of problem, I need to find a configuration of items. For example, here the configuration of the meetings or the time slot of the meetings that I can meet all the students within a day. something like this. Okay. In those situations, taking how many steps to figure out the configuration is not important. We don't even know the final outcome of the configurations. We don't know the final configuration, but we know there are some constraints that we should follow at the final configuration. So we can take all those constraints and configure it as the goal test. And we can configure our single state problem as each action is to add new items, add or modify gradually build up the configuration or making changes to the existing configuration. We can do things in two different manners. We can start off with a empty configuration and we gradually add stuff to it. For example, if I need to meet with 5 students, then I will make my reservation with 1 student first, and then I make another reservation with another student and so on. Okay, I try to eliminate the possible configuration of my meeting time with the students in a sequential manner. I start off with 1 student, arranging time slot for 1 student first, and then I try another student, and then I try another student, and so on. If I found that my configuration build up at the end does not satisfy all the constraints, then I start from scratch, but this time I start with another student, maybe in another time slot. Okay, we keep on repeating, generating the configuration from scratch. Okay, gradually starting from scratch, and each time when I come across a configuration that does not work, I restart and to create a new configuration again. Okay, so this is one way of building the configuration. Okay, and another way of building the configuration is that I start off with randomly assigning time slot for the 5 students, and each time I try to adjust the time slot of 1 student. I keep adjusting as long as I reach a point that all the time slot now doesn't conflict with each other. Okay. 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 So this is another approach for doing things. Okay. So single state problem with minor alteration in our perspective can be used to find a configuration of items that satisfy certain constraints. And that is vital when you are solving business problems. Okay? Okay. Imagine the example that I just told you, but this time is not about arranging the time of meeting between teachers and students, but rather than you are a secretary and you are trying to arrange the meetings for your CEO. Okay? If you are a secretary and you want to arrange the meeting time slot for your CEO to meet with other business partners, okay? Then the problem that I just told you is not a toy problem anymore. It is a problem that really exists in the business domain, right? Right? And we can solve it with single state problem. Okay? We just consider our steps taken to compose the configuration of meetings as the action that the agent can do, and that's it. Okay? Okay, so any questions? Okay. And here we use another example that is called the 8 queens problem. Okay? So in the 8 queens problem, what we are having is a chessboard of the international chess. And if you or I should just say chess, okay? International chess is not a formal name, okay? It is just I'm thinking with my Chinese mind, okay? So given that a chessboard right here, okay, this is the chessboard of the chess, okay. In Cantonese, it is called 國際象棋, so I just say international chess, okay, because I am just taking the Chinese name of chess as and then directly translating it, okay. In English, this is already called a chess, okay. And in the chessboard, we have 64 different cells, okay, and this board is composed of 64 cells, okay. It have eight columns and it has 8 rows, okay. See, it is in a square shape, okay. And what we are trying to do is to put 8 queens into the chessboard. And you don't need to know about how chess work, but you need to understand one thing is that the chess can move horizontally, move vertically, and move diagonally. So if you have chess pieces in the path block that is aligned in the pathway that the chess can move around, the queen can kill the chess. Okay. So for example here, if we consider this chess piece right here, okay, and in this slides, I have actually used right arrows to point out the direction that the queen can move, okay, and the queen here can move vertically, horizontally, and diagonally. So if you push any chess pieces along the arrow head directions, along the red arrowhead direction, then your chess piece can be killed. For example, if I put a chess pieces here, then my chess pieces can get killed by the queen. So our question here is that can we put 8 different queens in the chessboard that they do not kill each other? Okay, so for each queen, along the diagonal side, along the horizontal side, and along the vertical side, there should not be another queen. So this is the problem we are trying to solve. Okay, essentially we are trying to find a configuration of items. Here is the configuration of the queen pieces in the board. Okay, the positioning of the queens in the board that they do not kill each other. So this is the configuration of items they are working on. And the constraint is that they will not kill each other. Okay? Okay. You may think that this problem is a toy example, but you need to remember finding a configuration of items that match some constraint is something that we do daily in our daily life. One of the most clear example is arranging time for the weekend. If I only have one day available, and that day is occupied by other things, but I need to meet with 5 students in that day, I will need to figure out some time slot that I am free and the student are free, and I need to arrange an individual time slot for each student that I am free, the student is free, and other student is not taking the same time slot as well. Okay? Okay. So this is so-called the finding a configuration item that match the constraint. Okay, if you replace the problem as finding a bunch of time slot for the CEO to meet with his or her business partner, then suddenly it is a business problem that is very important in your life. Okay, okay. So this is what single state problem really capable of. Okay, to finding a path between 2 locations is just one example cases of the factory or the searching algorithm. If you are able to have a good representation of it, if you are able to translate your problem into a single state problem, then you can solve some problem that just by blink of the eye, you don't even know this problem can be solved by a single state problem. Okay? Okay? So any questions? So the key idea here is the key take a home message is that what in some situations when you want to solve a complicated problem, you don't necessarily solve the problem with the original intention. Okay, try to convert the problem in another representation. Sometimes it can help you to solve the problem easier. Okay, so this is a take away messages that you should learn right here. Okay. And here is an example solution. And the issue here is how we find the solution. And in fact, there are two ways to formulate the problem. And the first approach is so-called incremental approach. We gradually place the chess pieces into the chessboard. Or if we use the meeting example, that it will be gradually adding the meeting arrangement one at a time. Okay, until that arrangement doesn't work anymore. Okay, that is called incremental approach. And of course, if you try to do things incrementally and you find that at the end your original your original solution that is building up so far doesn't work, then you try to go back to scratch and try to add the things one by one again. Okay, so this is so-called the incremental approach. And the second approach is the complete state approach. You start off with a configuration that randomly generated, but the randomly generated configuration is not fulfilling the constraint. So what you do is you adjust the items to make the constraint satisfied, to make the constraint being satisfied. For example, in the queen problem, we start off with a chessboard, but we randomly assign the queens in the chessboard. Then we gradually move the chess pieces in the chessboard such that the queen do not kill each other. Okay, if we are talking about the meeting approach examples, then what we do is we just randomly assign time slot for the students or for the business partners. Then we gradually change the time slot for meeting of the business partner or students such that the meeting schedule is valid. Okay, something like this. Okay, and the ultimate goal, what we are doing here is that after we convert our problem into a single state problem, then we can just let the software to handle the rest. Okay. And here is the first formation is we just have a board and then we randomly assign a chess piece to it one at a time, and that's the simplest approach. But this approach is not a good approach because we have 64 powered by 8 possible combinations to consider. Okay, so our next approach is we take something here, we take the constraint here map. So we start off with randomly putting a queen chess pieces, and when we add new chess pieces, we also consider the newly added chess pieces matching the constraint. That is, we want to add the chess pieces in the chessboard, but the chessboard added should not attack the previous added queen. Okay. Okay. So by considering the constraint, when we are adding the queens, we significantly eliminated the state that we know is not relevant in our search. Okay. So the second formulation allows us to get to the goal state in a faster course, in a faster manner. Okay? Okay? So any questions? Any questions? But everything have a cost. If you want to put a chess pieces here, you will need to check whether your chess pieces is killing other queens. But if that checking process take a lot of time, then it is not worthwhile. Okay. Okay. We add the checking to reduce the amount of the states we need to examine. But if the test takes so much time, then it may not be worth it. So this is something you also need to take into consideration when you are writing program to solve a problem like this. If your test is too long that it doesn't make any sense, then the time saved of eliminating the state problem will not be able to compensate your extra time wasted in doing the testing. Okay, so doing the test to avoid meaningless states and also keeping the test simple enough such that it doesn't take too much time to execute is a balance that you need to consider. It is an engineering problem. Okay, you need to do some trade-off. Okay. So any questions? The idea is that we gradually add chess pieces into the chessboard and we make sure the queen do not kill each other in the process. But when we are deciding to solve a problem like this, you will need to consider the time needed and the memory needed to run the test in the first place. If the test is too complicated, then the time wasted to run the test will override the time you saved in avoiding the state that doesn't make sense. So at the end, you are not saving your time. So having tests to avoid exploring unnecessary states and making the test simpler is something you need to strike a balance. Okay? It's something that you need to consider. You want to introduce a more elaborated functions to avoid expanding unnecessary state, but in the same time, you should make your checking function be as efficient as possible to avoid wasting time in running the checking as well. Okay? Okay. And for formulation fee is that we try to rearrange, we try to randomly generate a chessboard with 8 queens in random locations. And each time we pick a queen and then we move, and then we pick a queen along a column and we move it. Okay? Okay. First of all, we generate a chessboard where each column contains 1 queen. Okay, we randomly generate a state like this. And then we do actions to pick a column, and then we move the chess pieces around. Okay, so this is what we do for the formulation fee. For the formulation of having a total state first. Okay, but of course this is not efficient because you may suddenly move the queen to a position that can get killed by other queens. Okay, so introducing Formula 4, the Formula 4 is we move the queen to a location that will not killed by the other queens. Okay. Okay. So this is what we are trying to do in formulation 4. Okay. So any questions? And if you notice something, our action sequence here is to manipulate the chessboard to generate the solution for us. Okay, and in these situations, what we care about is the ultimate configuration of the queries. So the time taken to run the algorithm is not as important as previous cases. In previous case, we are playing a game, so we want to make sure our sequence of action is as minimal as possible. But now we are working to solve a constraint satisfaction problem. So our time taken to find the right configuration is not that important for us. So the step cost of this problem is zero. Okay, because in this problem, the time taken to find the configuration is not important. Okay. Okay. So any questions? Any questions? And here are also some explanation of what I have do to how I implement the constraint checking. Okay, and you can try to understand what I write here. Because it's rather involved in the computation, rather involved in the programming technique. So I will skip as well. Okay, you can read at home. Okay, I put these slides here. So if you are interested to take a look on the coding that I released on the Moodle, you can refer to it. Okay. And you can also so this is what you will be able to find in the Moodle, as you can see here. So I have put down the equine second formation and the equine fourth formation source. So you can refer it at home to understand how the queen problem can really be implemented. Okay. Okay. So any questions? Any questions? If there is no question, then we'll briefly go over the next lecture, okay? Don't worry, I'll upload this lecture notes to the Moodle as soon as possible, okay? So now let's talk about informed or heuristic search, okay? So up to now, maybe you have some something in your mind. You have some thinking in your mind. You may think that the computer is searching the route in a rather silly manner, or rather mechanical manner. It doesn't care about whether the route will get to the goal state. You will not try to guess which route will get to the goal state first, and then prioritize that route. It do all the searching based on the existing information that it has. It doesn't consider which route has a high likelihood of getting to the goal state the fastest. Okay? Okay. But you may think but for human beings, we will try to do some guessing. Okay? For example, when you are solving a mathematics question, you have one or two ways to solve it to prove something. Okay? You will not try to write both proving approaches on your exam paper. You will try to guess which approach can really allow you to get to the end of the proof. And then you go with that route. Okay? So in humans, when we are solving problem, we will actually have some educated guess about the consequences of taking a route to solve a problem. Okay? Okay. And you may ask is, can we somehow emulate this behavior in the computer? And in fact, yes, we can emulate this behavior in our computer. Okay, and that is what we call informed search or heuristic search. So in computer science, when you ever see the term heuristics, this term will often means something that is not fully deterministic and something that is having some randomization or approximation in mind. Okay. So when you ever see the term heuristics used in computer science and data science, it often means an algorithm that is not deterministic or an algorithm that is having some approximation in nature. Okay. So we all the algorithm we just talked about in the previous lecture, notes, is uninformed search. But now we talk about informed search. Okay. So in uninformed search, okay, you essentially search all the you essentially conduct the search, without any knowledge of what will happen in the future, right? So if we go back to the lecture 3, when we are having a search tree like this, we are mechanically selecting the nodes here for exploration one by one. We don't care about which node has a higher likelihood to get to the goal state. Okay? All these nodes here, we don't, when we are running the building the search tree using the algorithm we just have been talking about, those algorithms doesn't calculate how likely a node here can get to the goal state. We treat all the states as equal. We don't have a measurement to measure how likely these nodes can get to the goal state. Okay, can get to the goal state, and then we prioritize that. No, we never try to compute how likely each node can get to the goal state and prioritize that. We just mechanically go through them one by one. And the major differences of how we go through this node is the ordering of the exploration. In breadth search, we explore shadow node first. In the depth search, we prioritize deeper node first. For the uninformed, for the uniform path search, we prioritize node with the lowest path cost up to the node. Okay, up to the node that we want to explore. Okay, so all these methods, all these algorithms do not make an educated guess on how likely each node here can get to the goal state. The principle here behind is that if we can have somehow a very good educated guess on which node here can get to the goal state faster, then we can follow that educated guess to explore that route first. Okay? If our educated guess is good enough, then we can get to the goal state without doing many unnecessary exploration. Okay? Okay? And that is what really the informed search is trying to do. We introduce some function to estimate how likely each node at the edge can able to get to the goal state. Okay, with what cost? Okay, we have a cost function that estimates the cost needed for a node to get to the goal state. Okay, and we use that figure to prioritize the node for exploration, and that is the ultimate concept behind the informed search when compared to uninformed search. Okay, in uninformed search, we just prioritize the node mechanically based on the information we already have. In informed search or in heuristic search, we try to have a function that estimates the cost for each node planning for exploration can get to the goal state. And we choose the node that have a lower cost, they have a lower estimated cost to get to the goal state for exploration. Okay? is essentially heuristics are the know-how obtained through a lot of experience. Okay, so one example that we can talk about, is playing chess. When you are playing, or I would say when you are playing card games or board games, okay? Or for local students here, I don't know if nowadays you still play games like this, okay? We just have the Chinese New Year, right? Okay. When you have the Chinese New Year, you may have gathered with your families, okay? So maybe in your generation this is not common anymore, but in the older generation, okay, when people are gathering together in Chinese New Year, what they will do is they will play mahjong. In Cantonese, that is mahjong. Okay. So I don't think your generation will enjoy playing mahjong, but I think your parents may enjoy playing mahjong. Right? So at least you know what a mahjong is, right? So when you are playing mahjong, you would need to guess what is the card that your opponent needs. Okay? So for example, if you are experienced mahjong player, then you can kind of guess what is your opponent wanting to have based on the card it discards. Okay? So for example, if the player is discarding a lot of I should say it angry. So if you can guess what your opponents want, what kind of cards that your opponent wants, based on what kind of cards that the opponent disposes. For example, if your opponent doesn't discard any string type card, okay, that is in Cantonese, that is sort, okay, okay. Then if your opponent doesn't discard any string type card, that is sort card, okay, that's also okay. And then you know that probably he wants the string type card in order to get okay, that is in order to win the mahjong game, okay. So all this would involve experience. If you are experienced in mahjong, you can kind of guess what your opponent wants, and you can kind of compute the exact card that your opponent wants. Okay. When you are playing mahjong, for example, your upper opponent, your 上家, okay, is keep discarding other cards but not discarding any string type card. That is, your opponent doesn't discard any shorty, okay? Then probably means that your opponent needs some shorty, okay, needs some string type card in order to win the mahjong game. And you can even guess what card exactly your opponent needs. For example, it needs the 3 string card that is some sort to win the game. Then you will try to avoid discarding the 3 string card. That is, you will try to avoid putting out the some sort, okay, such that your opponent will never win. So you can prevent your opponent winning. Okay. So that will involve some sort of guessing game, right? You would do some mental calculation in your head to figure out exactly whether your opponent needs some sort or sort, whether your opponent needs 3 strength or 5 strength card. Okay. So in that situation, that is a kind of heuristics. Okay. So for foreign student, maybe you think about this. Okay. When you are playing poker, okay, you will need to guess what kind of card that your opponent is having. Okay? If your opponent is, if you can guess what kinds of card combination that your opponent is having. If you guess your opponent is going to have a flush, then you will not try to raise your bet. Okay, so all these games would involve the guessing, involve calculations, involve guessing what your opponent is having. Okay, and that is something that need to take years to develop, and we'll call them as heuristics. Okay, and if you are experienced enough, then you can immediately figure out the answer without really go through the step of thinking. Okay, so we want to replicate this kind of instinct in our computer, and to write algorithm, to write function that estimate the outcome of something with a very low computational cost, that will be called heuristics. Okay, heuristics is as simple as this. We try to come up with a function that can calculate, that can estimate the outcome of something with a very low computational cost, far lower than actually doing the computation, then that will be called heuristics. Okay, and the next time we'll go through what is how we can use heuristic to do our search, and if we have time, we will also talk about algorithms that beyond classical search as well. Okay, and I think this is the good time for us to stop today's lecture, and we will be able, let's stop the recording, and this